And we have great speakers for this last session. The first one is Professor Kihwan Kim from Tsinghua University in Beijing, who will tell us about his great experiments in trapped ions. And I will warn you 5 minutes before, and you can start.
Together with all the other speakers, I also feel very thanks to Enrique for having me in this wonderful conference for the quantum simulation and computation. I really had a great time, and also thanks a lot for your patience until the end of the session. I hope I'm not fully sure, but I can entertaining a little bit you guys. Yeah, I'm going to talk about really simple experiment, and already you've been here in the poster session, also just before about the Rabi model experiment. So I hope this topic itself not that difficult to think about, I hope. So first of all, I want to introduce my wonderful students. Mostly these works done with the students, and we don't have yet postdocs. And at the end, I also want to advertise our groups. We are looking for also good postdocs and so on. And in particular, this work case, reduction lead all the things. And so these works mainly proposed by Enrique Solano and Lucas Namata. And Julian visited us about more than 2-3 weeks, and we had a really great discussions and so on. And we following this Enrique's proposal very strictly. And so we already hear many times about the Rabi model. So Rabi model is the simplest model that you can imagine between the atom and the field or light interaction. And so this is the most simplest model that you can imagine between these two interactions. So I thought it's very simple things and nothing much interesting going on, but I'm really surprised a lot of people are doing this kind of model simulations and so on. And for me, it's also very interesting because many people now doing quantum simulations and so on. And in trapped ion community, mostly we are doing spin model simulation, although maybe other groups are doing, other platforms do something different one. And now we are also including not only the spin part, also the mode part together. Maybe it's one of way to increase the Hilbert space without much number of qubits. Anyway, here is the brief the part of the simple experiment, the Hamiltonian of the Rabi model like this. So the first spin part, the two-level atom, and then the field part is usually it's a light field. So I have just had a quick discussion with Uwe Fischer. So usually this is light, and then some light atom interaction. And we cannot say that we realize this real Rabi model. We basically simulate, but before that, I may just briefly introduce what's going on. And we learned Enrique initiate this pointing of this Rabi model has a deep, strong coupling region exists. So the horizontal axis is the coupling strength. And since he pointed out many people's, many platforms like a false superconducting platform and some photonic system, mostly up to now the all superconducting systems pushing increasing the coupling strength. And this green one is our work. And you already heard the talk by Matthias in Garcia-Ripoll groups as well. And in our case, we don't have any light field, or we have a simple vibration. So our system roughly looks like this. We have some standard four trap. Already you may see from the Rhinos and also Guido for their wonderful presentation. So we have some number of ion, and then for us, this single atom is really the representing one qubit. We just choose 2-level, very nice part, and works as a qubit. And this one is inside basically a good harmonic confinement. It's a little bit misleading. We use just one atom, not many of them. So it's a simple one. And this one atom, we can think it just connected to a spring. So that's all mostly we have. And in this system, again, we don't have any light field, but we have some vibration, harmonic oscillator. So we have this the light part replaced by harmonic oscillator. So how we can do it? First of all, this spin is again from the atom. So this spin part is more or less related to like this. And then this harmonic oscillator, we are working in quantized rhythm. So the well-defined equally spaced ladder exists. There's a little bit difference of the spin, half, but anyway, it works as identity eventually, so it doesn't matter much. And now this interaction part, so the vibration and spin, in general, there's no interaction. But if we take some specific rotating frame of this one and apply the laser beam, so the one case may be the little bit smaller than the spin frequency by trap frequency, then we can create the so-called the Jaynes-Cummings interaction. So when spin is reduced, the phonon is, our case phonon, vibration excited. And when frequency is a little bit larger by this certain frequency, trap frequency, and then it's called the anti-Jaynes-Cummings, naturally not exist, but we can engineer such kind of Hamiltonian as well. So the spin increase, also the photon or some excitation increase. So this kind of control is not natural. Just when we apply the laser beam with a certain frequency, only that time it exists. So in that sense, we are doing simulating this light-matter interaction. So we don't have any natural interaction, but we just engineer by controlling the laser field, intensity, and so on. And you can easily imagine that when you add this red sideband, blue sideband parts together, it's very similar to the Rabi model part. So it's somewhat, you can have some sense that how we can realize a Rabi model. One thing I have to say is this one is taking the rotating frame of this guy. So when we have a rotating frame of this guy, we will not have any of this the spin part and the bosonic part. So we have to take some careful rotating frame. So what Enrique pointed is like this. So when now our frame is the rotating frame in the original just non-interacting Hamiltonian. And here, if we have a little bit detuning of the blue sideband and red sideband, something like that, and in that frame, our Hamiltonian looks like this. And no spin part and so on. But on top of that, so this is the Hamiltonian. So we have some control parameter of laser detuning, and then the intensity. On top of that, if we take the one more proper rotating frame, that's all that Enrique pointed is, then we will ended up this kind of Hamiltonian. So what that means is, if we now compare to the original Rabi model Hamiltonian, so this blue sideband, red sideband detuning corresponding to this spin frequency, and then the subtraction is related to the mode frequency, and the coupling strength exists as it is. So the same as left frame. So that's the main point of this simulation. So if we take the proper rotating frame, and then our Hamiltonian, although it's existing in this particular rotating frame, not the left frame, but it's the same as the Rabi model. And in experiment, some technical reason, we always choose, mostly choose this red detuning is 0. And this coupling strength, put it as big as possible. And then only control this blue sideband detuning. And by just controlling only one parameter, we can reach all the possible rhythm of the Rabi model. And this is one of particular result that the ratio is really small. That rhythm is called the James Cummings or the weak coupling rhythm. So in that case, also first of all, I have to point, although our Rabi model exists in the rotating frame, not the left frame, but the measurement that we do is basically related to the spin excitation. We can just directly measure because our rotating frame anyway this kind of form. So the rotating frame's spin excitation and left frame's spin excitation all same. So it doesn't matter for us. So simply the Guido showed the either spin is bright or dark. Based on that, we can just in single shot get the spin information. And the phonon part also is commuting with the rotating one. So the left frame's phonon and this Rabi model's phonon, all same things. So we can easily measure this phonon distribution by looking at the blue sideband transitions and the Fourier transform of these signals. So this is the coupling strength is really small. In that case, I have to remind you again. So all we control is blue sideband detuning. So red sideband is resonant, blue sideband is detuned. So as you can see, this detuning is larger than the coupling strength. Then that's all we need. In that case, we expect only this James Cummings term remained, and it's very easy to understand in our system like this. So this is the Hilbert space for our system. So this line is the spin down, this is the spin up, motional 0, 1, 2, and so on. It's just same as Reiner and Guido's picture. And now red sideband is resonant, and the blue sideband is far detuned compared to this strength. So as you can imagine, in this region, all happening is the dynamics of between these two guys. If we prepare start here, and then just a simple Rabi oscillation going on, and nothing else. So that's what we observe. So the excitation from the up, just a very nice Rabi oscillation, and then the phonon is excited and not excited, just anti-correlated with spin excitation. And when we now increase the coupling relative ratio of this guy, G over actually omega m, so then we should see the coupling component to the anti-rotating frame. So in our case, it's like this. So now the detuning is relatively now smaller than this coupling strength. So this is now have some coupling effect. So our oscillation not happening only this guy. So the little bit leak to the other side, and also maybe a little bit as well. So in this so we can easily achieve this so-called ultra strong coupling region. So this detuning is still smaller than the coupling strength, but relatively not that small like James Cummings. And in that case, as you see, it's not anymore nice Rabi oscillation, but something happening you can see. And here the experimental data and the theoretical expectation of this evolution is where match each other. And for us, the knob is very easy to control. So just put the detuning even more closer to the resonance, then we can easily make the deep, strong coupling rhythm. So in that case, now this not only confined here, but also excited, and even this one goes here, and so on. So now this dynamics covering many of the Hilbert space. So as we expect, the evolution looks getting more strange in the spin part, and also the phonon part as well. And also then so the first signature that about this Rabi model, when we go to this coupling strength getting larger and larger, and if we add all this spin excitation and mode excitation together, and the James-Cummings rhythm, everything just conserved. But when coupling strength increase, because of the effect of counter-rotating term, the total number of excitation is not anymore conserved, and getting more and more increase as we expected. So this is a very strong signature that we really realized the ultra-strong coupling or deep strong couplings Rabi model by looking at the breakdown of this excitation conservation. And in this kind of dynamics case, the one of particularism, like when this blue sideband detuning and red sideband detuning has a symmetric, and then in that case, the spin part effectively vanished. So it's a little bit strange, like no spin, but somehow the actually no spin, spin just degenerate, no energy difference, but still interact with light. So it looks a little bit confusing things, but we have to admit that this is a very typicalism of trapped ion community. And the trapped ion community, we do a lot of this geometric phase gate or Mormon-Jerenzen gate and so on, all is using this kind of parameter. So before Enrique pointed, nobody say about Rabi model, but it's kind of related to Rabi model. And even extreme, you may know about Dirac equation simulation, that also kind of realizing the infinite coupling strength of Rabi model and so on. You can interpret it like this. Anyway, the main idea of this kind of dynamics in our this rotating frame idea. So now the first now this detuning is symmetric. So the first is maybe the red detuning, and this is twice detuning and so on. In that case, this kind of bouncing back and forth of phonon number wave packet expected, and we can understand as like we have some harmonic oscillator, but the force is a little bit detuned. So in even classical case, if we simply spring, but now if we drive the spring a bit higher frequency or a little bit smaller frequency, then the motion is excited and reduced. Also momentum excited and reduced. So this is almost equivalent to this bouncing back and forth of phonon number wave packet. And the only difference is now this case happening only the photon side, but this the Rabi model case within this kind of parity chains. The same dynamics happening only inside the parity chains. And anyway, we have to say that this is very similar to the quantum gate of the trapped ion community. And indeed, also we observed very similar behavior as well. And the superconducting community also see very similar things. And you know, since this is kind of related to the trapped ion many operations, so we want to do something more. And we found this Enrique's paper really nicely. So we now think about this one, this simplest Hamiltonian, as a kind of one system, and we want to study this one like a really existing system, although we are doing simulation. So we are thinking about some ground state preparation and so on. So when we have some James-Cummings rhythm, and as you can see here, the spin down and the phonon zero is obviously ground state. Once your state is here, no excitation will happen. This is a lowest energy level, but now the coupling, the relative coupling strength is increasing, or the detuning is very close to the next level, and then this is not anymore ground state because it's connecting the other way as well. So the ground state of this guy is very complicated, and since we demonstrated all the coupling rhythm by simply controlling this detuning, so we have all the access whatever we like. So we start from the simple Hamiltonian when G is really, really small. So J is Cummings rhythm, and then just increasing the G, whatever we like. So that's how we did. And we realized in our experiment the coherence time and many things are limited. So we have to optimize this increasing the parameter of this relative strength. It's very small to the 1 or even larger, very carefully. So we found this this motional mode frequency is, we all control is motional mode frequency. So when motional frequency is big, and we just ramp really fast, when motional frequency is small, ramp slow, something like that, where we can optimize the times of our this adiabatic evolution. So depending on the situation, we ended up this motional, this ratio is 1.2 or 1.3, and up to the 2.0, we reach it. And this red one is our expected fidelity, pretty decent, we think. So this is one of the particular evolution example. So we basically we decrease the detuning or increase this coupling ratio during certain times, and we observe the spin evolutions as we expected. And at the end, now the only difference is we measure the spin correlated phonon distribution. So we just projected which spin it is, depending on that spin, what will be the phonon the distribution it would be, just we observe like this. And then as we expected, so this is one of good the manifestation of we ended up the ground state of this Rabi model Hamiltonian. And as we expect, this ratio is increasing, the more phonon number would be involving. So up to the 2.0, we just extended. And this is the red is the ideal case, green is including our some experimental imperfection and so on. It's more or less we're in agreement. And once we do this one, originally we want to measure the Wigner functions of all this, tomography of all this, but some other technical reason, I hope some of you figured it out, but we couldn't measure the Wigner function. And but this clearly, the spin and the motion is correlated. So we want to see some kind of entanglement. So this ideally, if it is really quantum phase transition and ended up some nice ground state, then we should have some entanglement between the phonon and this thank you, phonon and the internal state. But anyway, the time's up, so I cannot explain too much. But main idea is without the measuring whole things, we just somehow estimate a lower bound of the whole Hilbert space, and then we just look at the spins, the mixture, purity. So if a whole space is more or less pure state, but only just we look at the spin part is mixed state. This is a good indication this spin is entangled with other phonons. So by that way, we clearly observe some entanglement of our spin state. And then we apply this technique to the spectroscopy, imitating like this system like a real material. So we goes to what we do is, for example, this is, for example, the ratio is 0.3. So the automatically go here and adding this excitation. If no excitation happens back, then the original the ground state comes. But if some excitation happening, then we do see some changes. So by that way, we see some excitation like this and see very nice agreement with our expectation. So that's mostly about this Rabi model, Hamiltonian, and also with the NK, we had some simulation of involving phonons with this the field theory related works. Right now I had the works as well, and our case encoding is different. So the ferromagnetic, anti-ferromagnetic, and bosoning mode is different encoding. In that case also, we do see very similar like fermion, anti-fermion the collide and boson excited, and also the indon is very similar to the strong coupling regime. So this bosonic mode is not at all conserved regime, and so on. We nicely measure it, and maybe also we do some chemistry experiment as well. But anyway, eventually we want to extend our system to like this and see more interesting dynamics, including phonons as well. And thanks for your attention. And also, yeah, we are looking for postdocs. Thank you.
Questions? We have time for a couple of questions. Yep. The competition of Maryland.
Thank you for the very nice talk. Have you explored the regime where you have different Rabi frequencies on red sideband and blue sideband? And is there anything interesting there? Like, there are some experiments where they see squeezing in this regime.
So if the red sideband, the blue sideband strength is different, then it's deviated from the Rabi model. So but some of referees ask us what kind of effect would be and so on. So we have to, when we measure the intensity of the red sideband and blue sideband together, it's never be perfect. So we add some other error part and so on. But I don't know that ended up some nicer dynamics. But in terms of errors, we analyze carefully. And in our main observation, that's not a big problem within our experimental calibration.
Yeah, thanks for these impressive results. I was wondering, what are the prospects of generalizing this from the Rabi model to the decay model? We can go to the decay model in principle, like so before, all we did is using a single atom and applying the blue and red sideband and observe some things. And then our natural extension could be now adding more ion, and then just maybe globally exciting, then maybe very similar to decay model. And if we just individually exciting, it could extend many models, like including Holstein model and so on. So it could be the very general system to perform including decay model, many other the simulations, including phonons.
Okay, then thanks again, Kihwan.